Not yet.
Try aiming this way.
Yeah.
Is it enabled? Is it doesn't work? It needs to click on the screen. There you go.
There we go. Okay.
All right.
All right. Hello, Open vSwitch and OVN community. My name is Frode. I'm here on stage with Martin, and we are part of the OVN engineering team at Canonical. I'm also having Felix from Stackit here, because this is one of those sections where we have combined two talks into one slot on the same topic. We are trying to integrate OVN into the network fabric at layer 3, specifically with the use of BGP. For the longest time, we have had requests from users for ways to doing that. And we took a look at the options available in the community, and we didn't really find anything that matched our requirements. So we decided to start a project to get this into OVN natively. And we from the beginning, we did our planning. Now it's not working. Yeah. Let's see. Okay. Yeah, we started our planning in the community. I believe the first time we brought this up was in the monthly audio video meeting. And we invited a community member, Vladislav, to discuss some of his requirements for the cloud that he's running. And it snowballed into a lot of meetings with ever more participants. I'm not sure if the meeting has ever had that many participants on this topic, so it's a popular. We also sent an email to the list to discuss our interpretation of the requirements, and this received a lot of feedback from the community. This thread alone had 31 replies and 9 participants. So thank you so much for everyone who participated in that. And yeah, let's dive into some of our motivations for this. So if you look at what OVN and OVS does, if you boil it down to the very core, the purpose of it is to get packets in and out of virtual machines and containers as quickly as possible. And if you look at the density of the servers that people deploy in their data centers today, that is a ever increasing challenge, and we have increasing bandwidth demand as a result. So having some sort of hardware acceleration in there is very important to us. We also want to build something once and use it in multiple projects. We support, OpenStack, Kubernetes, and LXD microcloud, and all of these projects can use OVN as their networking solution. And for our users, they want to be able to use layer 3 only network designs. And the things that gives them is things like resource location, where you get traffic routed to the intended destination of the packet without going through gateways or tunnels of any sort. And you also can do interesting things, such as using the fabric as a load balancer by announcing the same prefix multiple places, which is also known as anycast. Some of our users' motivations to do this is to avoid the many issues of large layer 2 broadcast domains. I'm sure anyone here running large operations have had their night's sleep taken away from problems with that. And some users also want to avoid the configuration complexity of running EVPN, which is essentially just running the overlay on the switches instead of on the machines. So let's drill into some of the requirements and what that means for the implementation. As I said, we want the data path to be hardware accelerated. The consequence of that is that the IP address, which is the next stop for the fabric, needs to be an IP inside the Open vSwitch data path. Otherwise, we can't make use of all of the wonderful things that Open vSwitch gives us. Integrating at layer 3 means adding an IP address to every host in your data center. And that's a lot of address planning and a lot of configuration. So we want to minimize that by using a mechanism called BGP, which essentially makes use of IPv6 linked local addresses, which are already there. Yeah, to solve that. We also want to support eZMP out of the host. essentially to because somebody wants to not rely on layer 2 bonds and vendor-specific multi-chassis lags and things like that. We need to support BGP authentication, which works by hashing IP header information. And the consequence of that is that we can't use network address organization to get the control plane traffic to the BGP daemon. And we also want to integrate with multiple routing protocol suites and minimize duplication of effort. So this is mostly for reference. This is what we want to do for 2503. We have some heroes in the community who have started some of this work for us already. So thank you, Felix. So maybe we get onto some of this as well. Who knows? And this is an overview of the current RFC implementation, which is on the list. And I'll now hand over to Martin, who will speak to some of the details of that.
Thank you, Frode. After the introduction, I would like to talk a bit about the stuff that already made it into the OVN, and that's a BGP control plane integration that's made it in as a experimental feature, but it's there. So as some of the goals that Frode already mentioned, we wanted to achieve that we could speak with the external BGP speakers, for example, on top of rack switches, from the chassis, and act as if our side of the BGP speaker was listening on a IP owned by a logical router port. Those are few benefits that we would get from that. So as in the routes would be announced with the correct next hop automatically, and BGP authentication that Frode already mentioned would work out out of the box. Another thing that we wanted to is to avoid implementing BGP inside the OVN codebase itself from scratch. It's not impossible, but it's at least impractical due to the complexity of the BGP protocol and the fact that there are already open source solutions out there that we could reuse. And yeah, this one already Frode mentioned, we wanted to keep this hardware offloadable. So take a very simple scenario like this. There is OVN chassis hosting logical router, and through a logical switch, it's connected to external network, and on this external network, there is top of rack switch. We cannot bind a BGP process to address of a logical router port, because the logical router ports cannot be bound to a system interface the same way that logical switch ports can be. So what we can do is create another logical switch port in the switch that is connecting us to the external network, bind that to a system interface, and stash that interface either inside VRF or network namespace. Once it's stashed in there, we can set the same IP and MAC address on the interface as is on the logical router port, and we can start the BGP process in there. Once the BGP daemon listens on this address, the last piece that we need is the BGP protocol redirection. So this is the actual feature. So this is something that can be configured on logical router port, and when configured correctly, it changes the behavior of logical switch in a way that, while regular traffic still flows to the logical router, traffic that is BGP and is directed to the IP address of logical router port gets redirected to our logical switch port instead. This causes it to show up in the BGP daemon, and the top of rack switch daemon thinks that it's talking to a peer that listens on the IP address of the logical router port. Right, so we can do a quick demo of this, and this would be a topology that we are going to be using. So the layout is from the top. There's external host. We are going to use it just for the testing network connectivity. Then there's a spine router. Below that is a layer of top-of-rack leaf switches, and on the bottom there are OVN chassis. There's a minimal configuration going on here. All of this is running on IPv6 link local addresses and BGP unnumbered. There's only IPv4 configuration going on here between the external host and the spine router. We are using micro-OVN to deploy OVN chassis, and the reason for that is that we have a branch of micro-OVN that builds OVN with some unreleased patches, mainly a work by Frode to allow route leaking from OVN to the VRF so that the BGP daemon can pick it up, and patch from Felix that allows routing IPv4 over IPv6 next hop addresses. Right. There is no CMS in here, so you will see some switches, some scripts that are there to mimic creating something like a VM, which is really just an interface stashed in the network namespace and has IP configuration applied to it. Right, and in the demo, we won't show the top-of-rack sleeve tree and chassis tree for more clarity. They are in the deployment, but they won't be in there. Right, so the same layout of external host on top, the spine on the bottom, top-of-rack leaves below, and chassis on bottom. In terms of configuration, there is very simple BGP configuration. Basically, the leaves are connected to the chassis and to the spine, and the spine is connected to the three leaves. On the chassis itself, all right, yeah, let's watch the BGP summary going on because we don't need to configure anything on the top-of-rack switches anymore. As you can see, the top-of-racks are connected to the spine, but there's no connection to the chassis because there's nothing going on the chassis. There's no network northbound configuration and really no southbound configuration, just three chassis. There are no network namespaces, no VRFs, and we can start using micro-OVN to enable BGP integration. It takes some configuration. It takes the name of the interface that provides external connectivity and IP address that will be assigned to logic router port. It takes VRF table ID and ASN for the BGP. Right. So once this is applied, we can see that the leaves BGP daemon suddenly started to have connectivity with the chassis. And this is what micro-OVN gave us. It created a logical router for us and the logical switch that connected us to the external network. It also triggered all the right configuration, turned all the right knobs. It told OVN to maintain a VRF for us, to redistribute NAT and load balancer IPs, and to redirect the BGP, well, in this case, BGP and BFD traffic. So yeah, we can see the VRF in here. And one more thing that micro-OVN has is bundled FRR. So it created a configuration for us. It runs inside the VRF and it redistributes kernel routes. So let's see the redistribution mechanism. We will add a NAT address to the OVN. It's going to be DNAT and SNAT. It's some external address mapped to a logical address that doesn't exist yet. And we can see that we have a prefix propagating all the way to the spine, and it gets installed into the routing table over the IPv6 link local address of the leaf router. Right, so we can try pinging it from the external host. It won't go anywhere yet because well, there's nothing representing. There's nothing behind this logical IP. So let's use some of those scripts to create something that would resemble a VM or a container. It's really just a network namespace and OVS ports stashed into it. Right, so that was created, but still nothing is happening. So let's see what's going on here. We can exec into the net namespace, and yeah, we see that we have an interface with the correct logical IP address. We do have even the default route, and when we do like a TCP dump of ICMP, we see that we have both receiving the requests and sending replies. So what we are missing? We are missing a default way out of the OVN. So we need to tell logical router that to send basically outgoing traffic through the link local IPv6 address of the leaf. And once we do that, the traffic starts flowing from the external network. Thank you. And yeah, thank you. And I'm going to hand it out to Felix.
Thanks a lot. And I'll try to present the problem from our perspective and solutions we have thought out for now. The problem space is quite similar, but it's not completely identical. So that's why I wanted to share it here as well. If I step quite. Okay. Let's see. Thanks a lot. So let's first quickly take a look at our existing external connection in our environment is currently working. We have an OpenStack environment with a lot of public or with a lot of projects that are connected to the internet via logical router, which are doing that. So there you see the internal logical switch that each project on our side gets with random IP addresses that we probably don't really care about in this case. There's a logical router for each project with a static route with SNAT and DNAT for the floating IPs for the VMs, and a logical router port with a HHSS group or gateway chassis because Neutron doesn't yet know HHSS groups. And then there is this large, horrible logical switch where all these logical routers are connected to, and where we earlier heard a talk that outbound is maybe not the greatest thing in the world. And here we go out to the local net port. Now, if we now take a closer look on how does this local net side actually work if we think in terms of these multiple chassis it's running on. So here we again have the logical router port of this project router, which is bound to a HHSS group. So it's basically active currently on the chassis gateway 1. Then we have the logical switch port, the logical switch public, and the local net port. Now, each of these gateway chassis needs to have one NIC or multiple NICs connected to a switch or multiple switches if you're using bonding or MLAC or whatever else. And we then expect there to be some kind of way from this one NIC from this server to this NIC of this server in the same layer 2 network. And as we heard earlier, layer 2 networks are evil, and I want to repeat, layer 2 networks are evil. And how then the fabric manages dynamic routing or switching in here is not too much of our concern here. Problems. Stretch layer 2 networks. Large layer 2 networks are hard because of large ARP tables. Moving MAC addresses, or if we now move here this logical router port, if it now fails over to this gateway, it takes over its IP address and it takes over its MAC address, which means we have a MAC move. Or if you have a EVPN network and it's flapping a little bit around because there's packets still going out gateway 1 because the OVN controller didn't reconcile at the same time as the one on gateway 2. Then you have MAC flapping, which might lead to the fabric blacklisting this MAC address, or at least getting weird things about it. Dynamic routing themselves, or announcing dynamic routes, is currently, at least in our environment, handled outside of OVN by the OVN BGP agent, but which is not too much integrated, and I mean it works for. And this bonding or MLAG stuff also works, but the quality of saturation of both links is not as good as we would have it with ECMP. So this is the idea we came up with. We back here have still the logical router for the project with its logical router port. This didn't change. This is still what is inside or individual for each of the projects. Then we have a logical switch public, which is still the same logical switch. So up to this, there's no change in the architecture, which also means there's no change in the view of the CMS. This is still the same. I can still plug ports into here in the same way as before. Now what's changing here is that we put in a logical router here named Magic Router, and we remove the local net port from here. This Magic Router can then on the one side run here on all chassis, and here have one interface per chassis, or one interface per or one LRP per interface per chassis. So we can do ECMP on this logical router, which also takes into account appropriate interfaces of each of the chassis we are sending traffic out. We can then bind them to a real public logical switch where it's really going to the local net port. And if we now just set a bunch of static routes here and a bunch of static routes on the network fabric, we basically have integrated OVN into the network fabric. And the first hop that, or the network fabric, can send traffic to any of these gateway chassis. And OVN will take care about sending them to the correct destination. So in case we would now fail over this from one host to the other, it's now the job of this Magic Router or this logical switch to redirect traffic from one chassis to the other, instead of the fabric needing to move traffic from one chassis to the other. Which means the fabric is completely out of the equation of failing over this logical router port. And this is the same picture also as before, just with this additional introduction of the Magic Router. So we see here this per project thing is still bound on a per chassis basis. We still need it because it's not going on there. It has connection tracking tables. Like, we can't easily have this on all nodes. That might be an interesting other topic, but like not for now. What we can easily have is this logical router here, the Magic Router, to on the top end towards the projects, be on all chassis, because it doesn't hold any state, and it also doesn't have any egress interface to a physical world, so it can run everywhere. The both interfaces here that we have need to be bound on a chassis because they need to go out to some physical connection, but we can have both of them active at the same time, because here we don't have any kind of connection tracking. Here we don't care about any kind of state. We just need all of them to be available at the same time. Basically, we can think of this as a physical router connected indirectly to this switch and to this switch. And this physical router would just behave like a normal physical router in a physical network fabric, completely independent of OVN. These NICs, this one NIC or multiple NICs, can then use whatever IP address they want on their like local peering network, and then run also BGP routing protocol redirect, just as we saw earlier, on top of them. And if we integrate this with route leaking as well as route learning, then we also don't need to set a bunch of static routes on this magic router as for egress traffic, and we don't need to set static routes here for ingress traffic. So we get rid of the stretched layer 2 network, we get rid of bonding and all that issues if we do it across multiple switches. We do failing over now by changing priorities of routes. So if this LRP moves from this chassis to this chassis, the only change the network fabric would see is it's less reasonable to go via this path, and it's more reasonable to go via this path. The fabric can still go via this path. The fabric can always choose a non-optimal path, and OVN will fix it for it. Which means also dynamic routing and this BGP integration is out of the equation for failing over this thing here at the top. So OVN can just care about this failover. And yes, we should change priorities of the route. When we move from here to here, the route priority needs to be better here, because otherwise we send traffic from chassis to chassis for no real reason. But if this happens like a second afterwards, then we just redirect traffic for a second. It's probably not going to kill anything, but we don't have a second of connection outage. And for egress traffic, or that's what I just talked about, ingress traffic. For egress traffic, here we have a bunch of ECMP routes, basically a bunch of ECMP default routes going this way, or going this way, or if you have 50 nodes, then 50 different ECMP routes. What we should prefer, if we are sending traffic from this project through this LRP, then we must be on this gateway chassis at the moment, because we're doing connection tracking there. So packet is here. So in this case, doing ECMP on this location is actually not an appropriate thing to do. If we can send it out locally, then why should we now on the egress path redirect it to another chassis to basically do it the exactly same thing? So this is about changing logic in the ECMP path to ensure that if we are already on a chassis that can directly put it out, send traffic out, then do it. If not, just redirect it somewhere else. If this also, this is the other case of if this doesn't work, this is not breaking a connection. It's just not as optimal as we could have it. All of this is currently available as a very, very, very early version in the OVN Fabric integration series on the mailing list. It doesn't have tests. It hopefully has tests by next week. But let's see if that actually works. And here we are exporting routes from logical routers to a Linux kernel routing table in a network namespace or in a VRF. We are supporting importing routes as well to the logical routers in the same way. So you can just run FRR in there, and whatever routes FRR installs in the kernel table, OVN will then pick up. Also, this here we have a LRP, LSP combination per chassis or per interface of each chassis. What's in here is a logic that you define this on the setting on the individual OVSDB on the local node, so that not that CMS needs to think about this topic, and the CMS needs to know about all these IP addresses and interfaces, but that the individual node can define this and Node will take care of the rest. This should remove the need for the CMS to actually change to support all of this. And that's it from my perspective. So thank you very much. And I guess we can go to questions.
In your demo, right, canonical demo, you had to add the route, LR route that towards the end to get the ICM to go back and forth. Why was it that route was automatically learned? So there's no integration where FRR adds the route into the gateway router or the distributed router by itself.
Yes, that's the part that's still missing. So we had a route leaking, but we did not have route learning. Yeah. So so the routes announced by leaf and spine BGP processes would not make it to the OVN. That's part of future work, but I just wanted to highlight that it's not in there yet, so it had to be done manually.
Okay, one more question. Isn't this like a chicken and egg problem in the sense that, let's say I want to bring L3 to the host itself, right? On the host itself, I want to bring L3 and then I install OVN and other Wi-Fi connectivity. How do we solve that issue? Because if BGP integration with OVN comes in later, how do I access the host? How do I bring L3 BGP to the host itself?
So it can be either through different interface. The interface that is not facilitating the north-south OVN traffic connection, or I mean, in this case, we were using IPv6 link local addresses to address between the a host, but I think that the answer is to use a second interface that is for management and not for traffic, for OVN traffic.
Thank you.
Sure.
So you are integrating external routing daemon, right? It can be FRR, bird, or anything. So you are giving that infra. So it might it'll directly install the routes into Linux kernel routing table. From there, we have to read and then reprogram. Like in case the future plan you are saying, right? One is the export part. I got it. So whatever the OVN we want to export. So the import part you were saying, right? Like how you are planning in future, like in case if you want to import anything to northbound.
I can speak to that briefly. So if you look at the patch set that Felix has put up, he's further developed the things that we started, and he's also added learning support. And I believe we just, in the routing table, there are properties for who inserted the route. So we essentially just look at the owner of the route. And if it's not us, then we read it from the routing table, essentially, if that answers your question.
Yeah, but so I'm asking in future, like let's say we want to import the routes learned by the external. So if external router is advertising some routes, right? So let's say we want to integrate into the northbound table, right? So that entire logical router will get programmed with the routes. So whatever the manually in the demo, the route is added, right? So that functionality is currently missing, right?
Yes.
So so do you have any thoughts? I'm asking, like how to integrate that into the northbound? Any external routes that we learned?
Yeah, so we're currently working on it. I think.
Yeah, I can quickly share it how it works on the thing I built here. Basically, we import a route and put it to a special table in the southbound database in this case, because from my learning with Neutron, I'm not sure how it is for other CMS. They expect more or less exclusive ownership of the northbound database. Okay. So if like we would move this information from FRR through OVN controller through the southbound database to northbound, then we would, at least with Neutron, probably get a conflict, and Neutron might delete this route again, which then creates weird results.
Okay.
That's why I choose to not do that. I'm not sure how it handles it for other CMSs. Maybe it's a lot more reasonable there.
Okay.
Same mechanism which learn routes in the availability zones. There is a special external IT interconnect learn route, something kind of this, and this road is in the northbound.
Mm-hmm. You mean that Neutron ignores it because some property? We could probably do that. Yeah. But for the functionality, North-D currently reads it from the southbound database and combines it then with the northbound data and with other stuff.
We're-
The response to the GMS is if you want to switch over to another mode. Like FRR itself has a problem.
We've hit time.
It will be running on every node.
Yeah, so FRR would need to be running on each node that sends traffic outwards.
If a node gets problem, then that's that.
Okay, we've hit time on this one. So I know there's a question online. Maybe we can answer it online, like, yeah, offline. So, all right, let's thank our speakers. This was good talk. Okay. All right, our next speaker is Rosemarie O'Riordan, and she's going to be talking about first-time contributions to OVN.